So let's get started. Okay, so let me pull up my Emma information. All right, so nice to see everyone here. Today we have a speaker, Emma Tolley, and she's going to be talking to us about dark matter. Emma worked at the LHC for a lot of years until a couple of years ago. She was studying the signatures of invisible particles and searching for evidence. But she She's leading the computing and data science activities related to the upcoming Square Kilometre Array Observatory. So Emma is going to tell us a little bit about that now. Take it away, Emma.
Okay, thank you. Let me just share my screen, find my talk. Okay, can everyone see the slides?
Looks great.
Great, thank you.
Beautiful flowers.
Oh, thank you. It's from Alice in Wonderland, actually, one of the painted backgrounds. Okay, thanks for having me, everyone. So I'm going to talk about searches for dark matter. So this talk will start by going down the rabbit hole of particle physics. So I'll talk about dark matter at the LHC, direct detection experiments, and also indirect detection experiments for a little bit, before going to what we can learn about dark matter with radio astronomy. So, what is dark matter? Well, there are various phenomena in our universe that don't quite match up with our current understanding of physics and cosmology. And this here is the classic example, the galactic rotation curve. And the basic example here is that when you plot the velocity of observations from starlight and observations from 21 centimeter hydrogen, so this is the stars and the hydrogen gas that are orbiting around in this spiral galaxy, the rotation curve that you get is quite different from what you would expect if you just assume that Newton's laws of gravity is correct, which is what the prediction is here in the dotted line. So it kind of seems like maybe there's more mass than it is expected, that it extends quite far beyond both the visible objects that we see, but also the 21 centimeter hydrogen gas emissions. And then here's another example. So this is the Abell 1689 galactic cluster. So here in yellow are various galaxies. And deep gravitational potentials sort of act like a lens and can warp light. And so all of these weird, can everyone see my mouse here? Just for pointing purposes. So here, all of these kind of like weird smears in the background, like this one here or this one here, these are actually galaxies that are behind this cluster that are being warped and distorted by the gravitational lensing. And you can actually map out what kind of matter is actually doing this gravitational lensing. And then you get this map here. So where all of this blue is sort of the invisible matter or invisible mass that is actually causing the vast majority of these distortions from the galaxy behind. So using this kind of measurement, we measure actually that there's much more of this kind of invisible mass that doesn't match up at all with the visible galaxies or any kind of gas emissions that we can measure. So this is a little bit strange. It seems to point to the existence of some kind of, new kind of matter, and sort of the jewel of the crown is the cosmic microwave background here. So the cosmic microwave background is sort of background radiation that was created back, very, very early on in the universe when free electrons and protons sort of all cooled down enough to combine and form neutral hydrogen. And then you have this background radiation that's sort of constantly reaching us, that is a snapshot of this moment in time in the universe. And for the most part, this is very, very uniform in temperature, but there are some very, very small fluctuations in what we call the cosmic microwave background. So what we can do is we can transform these small fluctuations into a power spectrum. So we can say, okay, well, we have these different magnitude of fluctuations and different scales of fluctuations. And we have a model for that as it would, that sort of shape of that power spectrum is driven by various cosmological parameters. So for example, the total curvature of the universe sort of changes the scale of the fluctuations, which you can see in this upper panel. The amount of dark energy changes the scale in the opposite way because dark energy is negative curvature. And then of course, the sort of total density of baryonic matter changes sort of this major peak here, and the proportion of all of the rest of the matter also changes the structure a little bit. Thanks to Planck, we can actually measure this full power spectrum, and therefore we can measure these cosmological parameters very well. What we measure is that the matter density of the universe is 0.14, but the baryon density of the universe is 0.22, so only 15% of the total matter density of the universe. So this sort of implies, there's something else here that's not, not made up of baryons. Electrons and neutrinos aren't really heavy enough to make up for the rest of this matter difference. So we say, okay, that must be dark matter. This dark matter would be 30% of the total energy density of the universe and 86% of all matter in the universe. So there's quite a big fraction of the universe, and we have no idea what it is. But we know what it's not. We do know a little bit about dark matter. So dark matter is non-luminous, so it doesn't, interact electromagnetically. It's non-interacting, or if it does interact, it interacts only very, very weakly. It's massive because it interacts gravitationally. And it has to be long-lived because, it was, there during the cosmic microwave background creation, and is still here in the universe today. Unfortunately, no known particles of the Standard Model satisfy all of these criteria. I mean, really, the thing that comes closest are the neutrinos. They're non-luminous, very weakly interacting, and long-lived, but they're really not massive enough to make up dark matter. They would be way too fast to actually stick around and create the galactic halos that we currently see when we observe dark matter in our universe. So there are various theories for what dark matter could be. One of them is the weakly interacting massive particle. And the idea for this would be in the early universe, WIMPs exist in thermal equilibrium with Standard Model particles, and then as the universe expands and cools, they fall out of thermal equilibrium, this sort of decoupling or freezing out, then leaves a relic density of dark matter. There's something called the WIMP miracle, where you have a particle with mass about 100 GeV, Standard Model interaction cross strength similar to the weak force of about 0.1. And then when you sort of plug these into your calculation of the relic density, you get 0.12, which is very, very similar to what the Planck telescope measured. So this sort of amazing coincidence is called the WIMP miracle, and is a very good motivation to try to look for WIMP dark matter. So one thing we can try to do to search for WIMPs is to recreate the hot and dense conditions of the early universe at the Large Hadron Collider, very close to where I am now, actually, over in Geneva in Switzerland. And we can do this by smashing two quarks together and then trying to look for the dark matter signature that comes out of that. The other thing, of course, is that we can model this interaction between the quarks and the dark matter particles with some kind of new mediator particle or mediator force. And so in addition to looking for the dark matter that's produced in this quark-quark interaction, we can also try to look for evidence of this new force that mediates the WIMP and Standard Model interaction. To do that, of course, we need to actually reconstruct the particles from these basic energy signatures. So this is an image of the ATLAS detector here, which I'm sure many of you may be familiar with. And one of the more difficult things to reconstruct is the missing energy. So trying to figure out, you have dark matter which doesn't interact with the detector at all, trying to find that imbalance in transverse momentum that's evidence that something non-interacting passed through your detector. And in the end, you end up with limits on dark matter that look a little bit like this. So on the left here is an example of limits for searches for dark matter, where you have the dark matter mass on the y-axis and the mediator mass on the x-axis. The mediator, of course, needs to be heavy enough to decay to dark matter, which is why it has this sort of triangle shape. And then we can also directly search for the evidence of the new force, which would have some interaction strength, which is shown on the y-axis here. And then the mass of that mediator particle is here on the x-axis. And you see these are pretty strong exclusions going down to like G of 0.1, although this is heavier on the mass side than what we expect for the WIMP miracle. Of course, this isn't the only way to look for dark matter. So we can also look for evidence of very rare dark matter annihilation. So we expect dark matter to be concentrated in gravitational wells, so such as the center of the Earth or the sun or the center of the galaxy. And so very, very rarely two WIMPs could annihilate to create standard model particles. And one experiment looking for this is the Fermi Large Area Telescope. This is a high energy gamma ray telescope looking for evidence of X-rays from space. And this is an example of a plot where they're looking for the signatures of two standard model or two dark matter particles colliding into BB bar. And then they look for the X-ray signature of that particular interaction. And this also managed to set pretty strong limits where we have the annihilation cross-section here on the y-axis and the dark matter mass here on the x-axis. And this is also compared to predicted dark matter limits from the high luminosity LHC. So this would be searches for dark matter sort of shown in these orange contours here. So sort of doing a good job of chopping up phase space here. And then additionally, if dark matter is everywhere and it interacts, although very weakly, with standard model particles, we can look for particle scattering with a local dark matter halo here on Earth. So what this would be is some dark matter particle coming in, hitting a quark, and then that quark is sort of recoiling and the WIMP goes off in the opposite direction. The way that we look for this kind of signature is through what we call these direct detection experiments, where we're basically looking for dark matter scattering off of nucleons, often in a noble gas. So for example, xenon 1 ton is a 2.3 ton liquid xenon detector under the Gran Sasso mountain in Italy. And they have this huge container of liquid xenon gas, and it sits here waiting for a dark matter particle to come through. When it recoils against one of the liquid xenon nuclei here, you get this sort of signature of electrons. You get as an initial scintillation signal here. And then as the electrons are sort of drawn up to this top layer of the liquid xenon, they interact with the xenon gas, which create a secondary scintillation signal. And so people use these two signals to try to distinguish between signal and background and look for this evidence of direct detection. Unfortunately, they haven't seen anything, but they do set pretty strong limits. So here we have the interaction cross-section on the y-axis and the dark matter maps on the x-axis. For very, very light dark matter, you don't really get much nuclear recoil, so you don't set super strong limits. But as the dark matter gets heavier and heavier, you set stronger and stronger limits. Of course, this plot is set assuming some fixed relic density of dark matter, some fixed density of the local dark matter halo. So as you make dark matter heavier and heavier, you actually have fewer and fewer dark matter particles. The limits start to get a little bit weaker. But still, these kind of experiments will set very, very strong limits. And what we can do is put together all of these results for searches for dark matter. So here in yellow, we have the LHC searches for dark matter. In these different shades of blue, we have searches for the new sort of dark matter mediator force at the LHC. And then in pink here, some of the direct detection experiments. And this is starting to exclude a huge swath of phase space here. There's not much room left for the WIMP. However, one thing to keep in mind when looking at these plots is that this phase space is actually very complicated. This is for a very specific choice of the couplings and also for a very specific interaction type. As soon as this changes, the entire picture changes a little bit. So here I've changed just the type of interaction from a spin dependent to a spin independent interaction. And already things are looking for a little bit better for the WIMP, especially in the low mass regime. So where do we go from here? The WIMP phase space is slowly starting to get chipped away. It's pretty crowded here with all of these experiments searching for WIMP dark matter. Well, there are an overwhelming number of possible theories for dark matter. It's like very, very difficult to choose one. We have strongly interacting massive particles. They're still not super strong, but stronger than weak. Sterile neutrinos, feebly interacting massive particles, where the feeble is different from weak, despite what you might think. Very light sub-GeV WIMPs, axions, self-interacting dark matter, and of course, everyone's favorite, primordial black holes. The thing is, though, that there are already quite strong constraints on many of these models. So for example, strongly interacting massive particles interact a little bit strongly than WIMPs. Most of these are excluded already by direct detection experiments shown in gray sort of spaces here. And then there are very strong constraints from the cosmic microwave background and also Milky Way satellites. So those are small dwarf galaxies surrounding the Milky Way. Additionally, primordial black holes were a very popular theory for a while, but very recent lensing experiments have excluded a wide swath of phase space. So this is an interesting plot where we have the mass of the primordial black hole on the x-axis, and then the fraction of the actual total dark matter relic abundance that primordial black holes could make up. So here at the top is where all dark matter is due to primordial black holes. And we see that, the vast majority of this space, especially this middle range, this is a huge mass range of 10 to the minus 11 to 10 to the 13, is basically totally excluded, unless you say maybe the primordial black holes make up like 1,000th of a part of the entire dark matter relic abundance. So at this point, primordial black holes are pretty well excluded. But maybe we should think a little bit about other motivations for dark matter aside from just the relic density abundance and not necessarily just looking at the particle nature of dark matter. So there are some current problems with current predictions for dark matter. So in modern cosmological n-body simulations, we simulate dark matter as a cold collisionless fluid. So this is called cold dark matter. It will be abbreviated as CDM in a lot of the other slides in this talk. So in terms of the particle nature of dark matter, this corresponds to WIMPs, primordial black holes, et cetera, everything that's cold and not self-interacting. This does a great job predicting the large scale structure of the universe. Like it's incredibly, incredibly accurate, but has some problems at the smaller scales. So there are three major problems, what we call the cusp versus core problem. So when we simulate low mass galaxies, the predicted dark matter halos are too cuspy. It doesn't predict enough mass in the core of the galaxy. What we call the missing satellite problem. So here on the right is an image of our very own Milky Way and some of the satellite galaxies, so these small dwarf galaxies that surround the Milky Way. And we can see on the order of 10 galaxies around us. When we simulate galaxy formation with the CDM model, we predict way too many dark matter subhalos compared to the number of galaxy satellites that we actually see. So this top panel here is an image of a simulation of a galaxy very, very similar to the Milky Way. All of the white points are dark, is like the distribution of dark matter. So you see the main galaxy dark matter halo, and then like thousands of subhalos for all of the dwarf galaxies, which is just way, way too many. You might say, okay, well, maybe actually the Milky Way is surrounded by thousands of subhalos that we can't see because it's dark matter is dark. But this leads us to the too big to fail problem, where the subhalos predicted by these simulations are just so massive that they must have formed visible stars to begin with. So we have all of these problems with our cold dark matter model. However, there are some, sure.
This figure that we had in the previous slide, like, is this what we refer to as galaxy clusters, or is that like something else?
So galaxy clusters is something else, yeah. So galaxy clusters will be clusters of galaxies like the Milky Way, whereas these are what we call subhalos. So they're often too small to be considered proper galaxies.
Okay, thank you.
Mm-hmm. Mm-hmm. So several non-standard dark matter scenarios have been proposed that resolve many of these discrepancies. So warm dark matter, it's not cold, it's not hot, it's just warm, which would be some kind of heavier sterile neutrino. Fuzzy dark matter, so this would be dark matter that's not a particle, it exists on a sort of longer size scale, like a photon, compared to an electron. So the natural candidate here is an axion. Freeze-in dark matter, so this is a dark matter that never existed in thermal equilibrium with a standard model particle. Instead, you create some kind of intermediate particle that then slowly decays to dark matter, like what we observe as dark matter over the course of the universe. And then, of course, self-interacting dark matter, and there are a lot of different particles in this candidate, but the basic idea is that, CDM isn't non-colliding anymore. You maybe have some more complicated dark sector that has a more complicated interaction with itself. And so one interesting way that we can try to look for these is totally changing topic here a little bit, but not quite, is radio astronomy. So radio astronomy is very different from traditional optical astronomy, where you're basically pointing a huge camera at the sky and taking a really nice photo. Instead, we have these arrays of dishes that can span miles and miles and miles. So this here is a photograph of the Meerkat telescope in the Karoo Desert in South Africa, which has 64 dishes. And the way this works is these two, we point these telescopes at the sky where there's some kind of true image in the radio spectrum of the object that we're observing. And this is taking a Fourier transform sample of the sky. Reconstructing that image at the end of the day is a very, very complicated task, but that's a topic for another talk entirely. What is very interesting is that radio astronomy is a field that is the sizes of these telescopes are rapidly increasing in size. So as an example, this is an image from 2004 taken by the Very Large Array of the center of our Milky Way galaxy. So here we have Sagittarius A, this nice blob, which is our very own black hole. We think this is a SNR here is like a supernova relic. We have 27 dishes here. And this is kind of the best picture that we can make of the sort of radio emission of the galaxy. Then, 1 or 2 years ago in 2019, when the Meerkat telescope first came online, this is the image that they are able to make now of the center of our Milky Way galaxy. So just with a factor of 2 more dishes, it's like a much nicer, way more impressive image. You know, we can see now all of this detail with this supernova remnant here. We see these like long filaments, which are electrons sort of moving through magnetic fields, creating this radio emission. And it's just like this incredible image with all of this additional detail. Part of this is because as you increase the number of telescopes, the complexity of reconstructing the image increases by like you know, as n squared essentially. So it becomes much more, you get much more data essentially, just from increasing the number of telescopes by even a little bit. And in a couple of years, we're working on building the Square Kilometer Array, or the SKA. This is a future radio telescope that's going to have not 27, not 64, but thousands of radio receivers. So this is an artist edition of what it would look like. It's going to be built sort of extending from the Meerkat site in the same desert with like these thousands and thousands of radio dishes. And this is a nice plot of the sensitivity of the SKA. So comparing to the JVLA, so an upgrade of the Very Large Array, and LOFAR, which is a radio telescope in the Netherlands. So the first phase of the SKA is going to be SKA1. We have 2 frequency ranges. So SKA1 mid is going to be a set of telescopes in the South African desert. SKA1 low is going to be a set of telescopes in the Australian desert. And then a second upgrade to that, SKA2, which is going to increase the sensitivity by like another order of magnitude compared to SKA1. So we'll be able to do some pretty impressive physics with this. And one particular example is analyzing the 21 centimeter line. So neutral hydrogen can undergo a decay called the hyperfine transition. Basically, you know, it can exist in 2 possible states. You know, you have the spin of the proton, the electron aligned, or a slightly lower energy state is to have the spin of the electron and the proton anti-aligned. Thanks to quantum mechanics, though, these can only be spin up or spin downs. There's no nice smooth transition. Instead, the electron has to quantum tunnel from the spin up state to, or the spin aligned state to the spin anti-aligned state. So this is a very, very rare transition. You know, the mean lifetime is 10 million years. But when it manages to do this transition, it emits a photon at a very specific frequency, so 21 centimeters or 1,420 megahertz. What's interesting is, thanks to Hubble's law, you know, cosmological redshift means that the 21 centimeter line, so anything emitting the 20 centimeter line is therefore redshifted proportional to its distance, not from Earth, which means that you have like this nice clear signal that you can, you know, it's kind of like a standard candle on top of some kind of smoother radiobacterium spectrum that you can use to map out like distant galaxies. And, you know, the farther back you look in these on these cosmological scales corresponds to looking farther and farther back in time. Additionally, looking at the 21 centimeter line tells us something a lot about the structure of hydrogen. So for example, these are 2 images of the NGC 6964 galaxy, one with the optical image where you can see all of the stars. And then when we look at the 21 centimeter line, we can see actually the full extent of the hydrogen gas in this galaxy. So it's quite interesting to map out the 21 centimeter signal throughout time. You know, we have this very clear signal, and so we can look pretty far back, and it's gone through an interesting history. So here, this plot's quite interesting. So the blue areas correspond to very, very dark. So not a lot of 21 centimeter emission, either because there was no hydrogen or there were no excited states of hydrogen to decay to do the hyperfine transition. So we have galaxy formation starting 100 million years ago. Then we have more and more gas accruing in these galaxies, which starts this ionization period where we have these sort of red structures here. So there's more and more 21 centimeter emission. And then things kind of cool down and calm down into the period we have today. So 1 billion years after the Big Bang. What we can do is measure the spatial distribution of this neutral hydrogen in terms of the 21 power spectrum. So doing the same thing where we look at the fluctuations and the density fluctuations of the 21 centimeter hydrogen emission. And this gives us a map that's quite similar to the cosmic microwave background, except extended in 3D, where that third dimension is now time. So what that actually looks like in principle, this is an image of the 21 centimeter image of the sky, though not at 21 centimeter. This is looking at, I believe, 74 megahertz, so quite redshifted. So we have some signals from our own galaxy, which we can see in this plane here, that are at 74 megahertz. And then, some other sources from other galaxies or from electrons emitting photons in magnetic fields. And then out here somewhere are the actual galaxies with hydrogen at 21 centimeters that's been redshifted to 74 megahertz. And what we want to do is try to create some kind of map of that structure. This is in fact a very difficult problem, much more difficult than measuring the CMB power spectrum, because of all of these foregrounds. So not backgrounds, but foregrounds, because they're actually between us and the signal that we want to observe. So this, for example, is a simulation where we have unpolarized foreground. You can see here, this sort of red line corresponds to our near and dear Milky Way galaxy. Polarized foreground, so those are mostly signals coming from electrons and magnetic fields in the universe. And of course, the 21 centimeter signal that we want to try to extract. The best way for us to try to separate these is using the fact that a lot of our foreground signals are smooth in the frequency dimension, but not our 21 centimeter signal. So we want to try to extract these fluctuations by doing this foreground subtraction and foreground removal. So to do this measurement, we are building the HIRAX array in South Africa. This is going to be a telescope that will be eventually incorporated not into SKA1, but into SKA2. And it should be able to do a very, very nice measurement of the 21 centimeter power spectrum. So this is just a plot of the small fluctuations in the power spectrum that we expect to be able to observe. When we're running with blue is when we run with 256 dishes. So not the full array here, but a smaller amount. And then also we hope to be able to upgrade to running with 1,000 dishes. So we'll get even better constraints. Of course, when the full SKA2 is up and running, we'll be getting like really, really powerful sensitivity that will really constrain this power spectrum as shown in this bottom plot here. And we can do some very interesting physics with this power spectrum. So it turns out that the distribution of hydrogen as the galaxy is evolving is actually extremely sensitive to your dark matter model. So this, for example, is a cosmological simulation. So this is just like a snapshot in X and Y for megaparsecs. So these are this is like what people call the cosmic web. So like a huge simulation of large scale structure of the galaxy, where you have these sort of dark matter filaments, and then where these filaments, like these lighter blobs, will be where galaxies eventually forms. And then where these filaments connect, you'll have massive clusters of galaxies. So those are the galaxy clusters that you asked about before. When we just do this model with cold dark matter, I'm not sure how clear it is exactly over Zoom, but get a quite a lumpy structure. There's quite a lot of scale here. If you say, okay, dark matter is not a cold collisionless fluid, but it's actually, let's say it's a 1 keV sterile neutrino, the structure looks very, very different. Now you have a much smoother distribution of hydrogen in the galaxy. And you can then calculate what sort of 21 centimeter power spectrum you would expect with this different dark matter model. And so this is a plot that's a bit difficult to parse with all of the different nomenclature compared to some of the particle physics ones. But essentially you have the difference between your warm dark matter model and your cold dark matter model on the y-axis here. Then you have, so K are the different modes basically of the power spectrum. So it's kind of the different scales of the fluctuations you expect to see. Z are the redshift. So you're looking at galaxies that are redshifted by a factor of 3 away, a factor of 4 away, a factor of 5 away. So basically looking at this in different slices of time. And then the difference, starting with a very, very light 1 keV sterile neutrino, and then increasing to 2, 3, and 4. And these are the different plots. And then the solid line versus the dashed line are basically two different simulations that the authors of this paper used to create this prediction. And then the sort of gray, blue, and purple shaded areas are the associated uncertainties for an SK observation of 1,000 up to 5,000 hours. So with a very, very long observation, we should be able to observe hopefully the difference here between like a 4 keV sterile neutrino dark matter versus regular cold collisionless dark matter. So very, very nice result from using the 21 power spectrum here. But it's not just sensitive to warm dark matter. We also had a recent publication by our collaborators at University of Geneva doing this analysis for fuzzy dark matter. So this is for axion dark matter. I'm looking for very, very light axion dark matter, where again, we have the modes in K on the x-axis here, and then the sort of density spectrum in the top panel of this plot, and then the ratio of the density spectrum to the cold dark matter density spectrum on the bottom. So we actually expect to be quite sensitive to fluctuations in the proportion of axion dark matter to regular dark matter. So as these different curve colors are changing, you're going from 0% of the dark matter relic density is due to axions up to 25% of the dark matter relic density is axions. And for SKA1, so this is just the first version of SKA, which should be running in, start running in 2025, in fact. We'll already be setting like quite nice strong limits on this axion dark matter, starting to get down into the grand unified scale axion dark matter models. And then hopefully SK2 will be able to set even stronger limits. So in conclusion, if you take away anything from this talk, I hope you, I hope the number one takeaway is basically that there's incredible complementarity between the astronomical, cosmological, and particle observations or exclusions of dark matter. There are so many different portals for studying a given model at different epochs and also at different scales. You know, you can combine these particle simulations with these cosmological simulations, you know, do a particle physics experiment to probe a different model or try to do an astronomical observation as well. The most popular dark matter theory, the WIMP theory, is slowly approaching exclusion, but cosmological models also imply that we should be rethinking the cold dark matter paradigm. And new precision instruments like the SKA will allow us to make measurements that were not possible before. So that's the end of my talk. Does anybody have any questions?
All right, thank you.
Clouds.
All right, do we have questions? Let's start with the students.
If you could go back to slide 34, like you had a map basically, yeah, the power spectrum. You may have explained this, but why is like the signal from the Milky Way galaxy like in a plane? Like how to interpret that?
Oh, this is because it's just looking at the, you know, we are basically, Earth is kind of like at eye level, it's like embedded within the Milky Way galaxy disk. So as you look towards the galactic core, that corresponds to this kind of very bright blob in the center. You know, if you look up, you're suddenly looking straight up from the Milky Way. If you look down, you're looking straight down. And then if you look from side to side, you're looking sort of within that plane. It's kind of like looking edge on at a Frisbee.
Okay, I understand. Thank you.
Mm-hmm.
I may have a very simple, quick question about the telescopes. Do they need to be aligned in a certain pattern? Because according to, look at the page 31, it looks pretty random to me.
Well, so it depends on the experiment that you want to do. So Hyrax, for example, you want a lot of telescopes very, very close together because you're not really interested in like taking really nice pictures of galaxies, for example. So that we have this grid of telescopes.
Yeah.
Or larger telescopes, like if you want to image something at a really, really high resolution. So for example, where's my Meerkat image? So like take this image and like reconstruct these specific filaments, and you're not interested in like taking a sort of wide, broader picture of the sky. Then you basically want to create telescopes that are as far away as possible. And so it's not exactly random. People do this in this kind of spiral structure. Although I think in this artist rendition, the artist maybe copied and pasted it a little bit randomly. But let's see if it's obvious in Meerkat. No, not so. But it sort of does this like spiral structure where you start at the center and then sort of spiral out like the shell of a nautilus, for example. And usually you'll have like
Okay.
several prongs. So 3 prongs is usually the orientation that people use. And then you'll have some sites, so you'll have sort of clusters of telescopes in like one area and then clusters of telescopes in some other area, so that you can like have like a really, really far separated observation here. It's all about trying to get, because this sort of phase, you want like a very, very large phase shift basically between these telescopes that are trying to observe the sky in order to get the highest resolution possible in your creation of the image.
Yeah, makes sense.
Mhm.
Okay, thank you.
I had a question. So with your, does this mean that cosmologists now have to go back and reevaluate the hot dark matter? Because I know recently they prefer the cold dark matter hypothesis.
Yeah, so the problem with hot dark matter is that like, and I don't know if I have a plot of the exact limit for how light dark matter can be, is that you don't have dark matter sticking with these galaxies anymore. Like basically if dark matter is close to relativistic, you really can't have it in any kind of, you don't get it sort of clumping and following galaxies or galaxy clusters in the way that we currently observe it. Cosmology is undergoing a bit of a revolution now, though, thanks to some other constraints for other parameters that are being measured. So there's this tension, and maybe I have this in backup. Yes, so there's this, people like, so cosmologists are currently reevaluating their model of how the universe observes, because there's this tension in the measurement of Hubble parameter, Hubble's constant. So there's this term, when you write down the equation for the expansion of the universe, you know, you have all of these pressure terms. So some terms accelerate expansion, like radiation pressure from photons or from dark energy. Some terms slow down the expansion of the universe, like the matter terms, because, you know, gravity is trying to pull everything together. And all of these terms are sort of driven, like the evolution of these terms over the evolution of the galaxy is driven by this constant H0. Recently, people have been doing studies where they're trying to actually measure H0, and through stuff like doing this 21 cm power spectrum mapping, where you can sort of measure quantities at different ages of the universe, because you're looking like at farther and farther redshift, which is farther and farther galaxies, which corresponds to farther and farther back in time. You can sort of measure these quantities at like different snapshots of the universe. And what they're finding actually is that H0 seems to be evolving with time. So people are like trying to come up with a lot of, I mean, there's a lot of uncertainty right now for cosmological models in general.
Hi, can you hear me?
Mm-hmm.
Okay, sorry, we've had some audio issues, so I apologize if you have to repeat yourself. So when we're looking at the graphs of the 21 centimeter hydrogen spectrum, I've got a couple of questions about those.
Mm-hmm. Which slide did you have questions on?
Earlier, all right, so this is the first one I have after the one after this.
This one.
Yeah, so my first question is, what's that big gap?
So this big gap is because the telescope is sitting on a specific location on the Earth. And basically there's one part of the sky that you can never see at any time of year.
Okay, just because it's in one hemisphere and it can't see.
Yeah, exactly. So it's just, it's like, it can't see like below, I think this must be a southern telescope, although this depends on the projection. So it can never see into, it can't see like past into the northern hemisphere. So all of these like maps of the sky will always have this big gap, which is why a lot of these telescopes are designed so that you have one telescope in the South Pole and another telescope, or sorry, Southern Hemisphere, not the South Pole, one in the Southern Hemisphere and one in the Northern Hemisphere. So for example, there are already a few telescopes. So like the CHIME telescope in Canada, for example, is like the sister telescope to HIRAX, which is currently being built and should be taking data very soon. And the HIRAX telescope is in the Southern Hemisphere, so it will sort of fill out this hole so that we can make like a full complete map of the sky.
Okay. Is there a reason you can't just like combine all the data from all the radio telescopes like that are publicly available?
To do the intensity mapping?
I guess to do any
Or-
of this stuff. You mentioned that there was like an n squared efficiency with something, but
Yeah, so I mean, you can do combinations of some of these radio telescopes and some of these observations, and that's a very common thing. The problem is that these observations that are taken need to happen at the same time. And
Okay.
often the way that observations work in radio telescopes, people are like granted an allocation for observation time. So some people may be doing these full sky scans, but some people may be just wanting to take a really nice picture of like one galaxy or a really nice picture of the Milky Way. So you don't have like one data set that was all taken at the same time from all over, from all these different sites. But for example, the image of the black hole that was all on the news like a couple of years ago, that was another radio observation. And they had like 6 telescopes or something like that, like all across the world. So some in Chile, some in the Northern Hemisphere, some in the Southern Hemisphere. And they sort of took a really, really long observation and then had the observation on physical hard drives that they then shipped to one central location. So they had all of the data available for them to build the final image of the black hole. So you can do these like combined telescope measurements, but they need to be observations that are taken at the same time so that you can do this reconstruction of the signal. Where's my image of Meerkat? Here, because you need to know the time delay between these, and they need to be sort of observing in the same way in order for you to reconstruct the image.
okay. So you basically have to ahead of time organize with all of the observatories that you want to use together.
Yeah, exactly.
Pointing at
Yeah.
one part of the sky, the weather has to be correct. In other words, good enough at different telescopes across one hemisphere. This might be a little bit different than the all sky survey she does, but in the case of EHT, you have to point these telescopes at one part of the sky, and the weather has to be good enough at all these stations in order to have these simultaneous observations that you then later go back and combine. That's another limitation to the
Yeah. So optical astronomy is able to take like much higher resolution images than radio astronomy because the wavelength is much smaller. Where's my optical versus radio image? But again, as you were just saying, it's very dependent on the weather being clear. Thankfully, with radio astronomy, the radio waves go right through the clouds, so we're not as dependent as the weather, but wind or sandstorms can cause a problem.
And there's lots of telescopes in deserts like Chile and Arizona. So
Mhm.
So I had another question about the slide right before that. Right before the one that I had the previous question.
Do you remember what slide number that was?
33, I think he.
33. Mhm.
Yeah, okay. So what's the y-axis on this?
Oh, so the y-axis, these are basically snapshots of a cosmological simulation. So they are sort of, as they're doing like a full 3D simulation, they're then just taking some plane in that, mapping what the hydrogen emission is, and then stacking all of those together.
Okay.
So that's why you kind of have these like blobs which like appear and then disappear.
Okay, so it gives an idea of like the clumpiness.
Yeah, exactly. Because like some of this is driven by like the large scale structure. So you have galaxy formation only happening in, I guess that's not happening here, but you have galaxy formation only happening in specific regions and reionization only happening in specific regions. And so that's mapped out by this simulation.
Cool.
All right, other questions? Maybe we can allow some non-students to jump in now too.
I have a question. Do you want to?
Yeah.
Yeah, sorry, Emma, we had a weird audio glitch in here, so now the students are all kind of taking turns next to my.
Oh, okay.
So early in your talk, you mentioned that ordinary neutrinos are a bad candidate for dark matter.
Mhm.
And later you said that a possible candidate for, I think, warm dark matter would be sterile neutrinos.
Mhm.
So I was wondering why, one is a possible candidate and not the other. I think you mentioned that the problem with regular neutrinos is just the sheer number of them, I think, could contribute enough mass but they're just moving too fast to like stay within the right shapes. Would we expect that sterile neutrinos would be moving slower? Or
Yes, yeah, exactly. So we think that regular neutrinos could make up like up to at most 1% of the dark matter relic density that we've measured, but the vast majority of it needs to be made up of some other kind of slower moving matter that can be, it just needs to be gravitationally bound basically in order to sort of match the, well, not this one where it's broken, but the, where's my other plot? Well, it needs to be gravitationally bound essentially to sort of match the larger scale structure that we observe. So the sterile neutrino would be some kind of fourth neutrino, sterile because it doesn't mix with any of the other neutrino states. And then that would allow it to be, you know, heavier so that you can give it a heavier mass. There is some limit though on exactly how light it can be. Unfortunately, I don't have that in the slides and don't know the exact number off the top of my head, but people are often testing like 1 keV models for the heavy sterile neutrino.
okay, so we would expect it to be heavier. Is that also why we expect it to be like slower?
Yeah, exactly.
Just heavier just means slower. Is there any like, would we expect them to like form at like lower energies, or is the slower speeds just due to expected higher mass?
So it's a combination. So because they're forming at, you know, higher mass, they should be non-relativistic. So it's totally driven by that. You assume that things are being made in thermal equilibrium where you're at some energy scale where you're able to create the sterile neutrinos. And then at some given like freeze out temperature, those need to be heavy enough just to be not moving relativistically, whereas regular neutrinos would be moving relativistically.
All right, thank you.
Mm-hmm.
I have a question about the xenon 1 ton experiment.
Okay,
So-
shoot. I'll do my
so
best.
If dark matter doesn't, yeah, that slide.
Mm-hmm.
So I think I remembered you explained it. Dark matter comes into this liquid xenon tub, and then does it hit a xenon particle and then creates a shower of electrons? Is that right?
Yes. Yeah.
How does that happen if it's not supposed to interact?
So the interaction can happen very, very rarely is the idea. Yeah. So you have, it's kind of like the weak force where because you have a massive mediator, it's very, very rare until you go above the energy of the mediator mass, and then it, you know, acts like a much, much stronger force. So you still have like a very, very rare chance of this interaction happening. And so these limits, so here on the y-axis, this is still, you know, this interaction cross-section 10 to the minus 43, 10 to the minus 45 is like a very, very small interaction cross-section. And these experiments are often sitting and just waiting for a signal over like years and years and years and years to like eventually set these limits. So it's an extremely rare process that they're waiting for.
And why does it happen with electrons as opposed to, I don't know, something else?
It's actually recoiling off of the nucleus, and then that ionizes the electrons, which then create the signal.
Okay, thank you.
I had a question.
Okay,
I
go
don't
for it.
know if I need to.
Yeah, come closer.
Sorry. I interrupted your question because I actually, like, when I see this, I had the same issue, was like, how, if it's not supposed to interact, how you see it? And I think the answer is, if it doesn't interact, we're all screwed, because it has to mix with some standard model particle in some way in order for you to detect it this way.
Yeah.
But
So one way that we know that it has to interact is, so this basically plot of the relic density. You know, if we assume it's created in thermal equilibrium, so that's it not being a freeze-in kind of dark matter. Basically, as you have, so this is a plot that shows this. So X is like as time is evolving, you know, you have the universe getting cooler and cooler and cooler. You have some number density, which then freezes out, and those are these dotted lines. And this freeze out sort of depends on what the annihilation cross-section is. The annihilation cross-section is proportional to the standard model interaction cross-section. So if you have a really, really tiny interaction cross-section, then you have a gigantic relic density. And so the universe would collapse into a black hole if you had way too much of these massive particles. On the other hand, if your interaction cross-section is too high, then you have like too little dark matter essentially, or too little such that you need WIMP dark matter, and then maybe like a smattering of other models for dark matter to make up your dark matter relic abundance. So we have from the relic density, and assuming that it was created in thermal equilibrium, we have some kind of basically limit on the interaction strength that it would have with regular standard model particles. So basically we say it has to interact somehow because it exists. Therefore, it had to be created in some kind of process, whether that's thermal equilibrium or via a Friesen process, of course, is completely unknown at this point.
I actually didn't get to my question, and there was another one in the chat. My question is very unfair because this talk focuses on the hypothesized particle nature of dark matter. So I'll be this guy because someone has to. What about MOND? I'm not personally a huge fan of MOND, but the theory doesn't seem to want to die. There was a recent paper, I don't know if it's on the archive or in a journal, where some MOND theorists claim that they can tweak their theory to match the CMB power spectrum, which was a huge deficit of MOND in previous times.
What's MOND?
Modified, M-O-N-D,
Modified Newtonian dynamics.
The idea
Yeah,
that you can
so
dark matter with just modifications to gravity rather than a particle.
So-
And I'll let you answer the question, but just to
Mhm.
actually ask it. So how does this fit into this picture? What do you personally think about this, et cetera, et cetera?
So I feel like I should have put an image of the bullet cluster and the bullet cluster gravitational lensing in here. So I haven't read the most recent MOND papers, but my impression was that MOND was killed by recent observations with these gravitational lensing and galactic clusters. You can basically look at instances where sort of galaxies or galaxy clusters have collided, and you'll basically see that the dark matter mapped out by gravitational lensing sort of separates out a bit from the actual visible matter. So these are pretty good examples that it's some kind of particle or matter and not just modified Newtonian dynamics. Additionally, there's the classic, Newtonian dynamics has matched very, very well on like all of these different scales that we've measured so far. So it's kind of, I guess it's like a personal preference if you say, okay, well, we just need to add a new kind of species of particle. And, we've been discovering new particles, as late as 2012. So it doesn't seem that wild or crazy versus modifying this theory of gravity, which is thus far held up very, very well under experimental tests, assuming that you have some new kind of matter. But yeah, I think the bullet cluster is very strong evidence that MOND theory doesn't really hold up. Unless there's like a recent explanation where they can explain the gravitational lensing effect here sort of separating out from the visible galaxies.
Yeah, I don't know. I think that there is, but the issue is that they have to make these ideas very convoluted. In other words, even though we were considering, like, for example, modifications to the CDM paradigm, I think when they start throwing in unmotivated physical parameters into their MOND theories, right? Because they go beyond MOND, there are relativistic extensions of it, et cetera, that it's not very favorable, but they don't seem to want to quit because they keep publishing papers. So I don't know. But anyway, thank you very much.
Have you heard about conformal gravity? Is that a MOND theory?
I think conformal gravity is the same.
Let's
actually-
focus on the speaker. I think we still have a lot of questions for the speaker. All right. Does anyone on Zoom want to ask Emma a question?
There was one in the chat.
Oh yeah, there was one in the chat. I can read that aloud. Okay. Oh gosh. Let's see. Sorry. Okay. So we have the question. So where would the energy for that recoil off the dark matter? No, recoil of the dark matter off the nuclei come from? Does dark matter use non-dark energy? I don't think I quite understand the question.
Because there's dark matter, dark energy. So is dark matter associated with dark energy?
Oh, yeah. Dark energy is a separate phenomena.
Yeah.
dark energy we think is like an energy field, but it's a distinct phenomenon from dark matter. That's another separate talk entirely. Yeah.
Dark in the sense that both of them are things we don't observe directly with our telescope, but otherwise unrelated.
Yeah.
Yeah, it was
Something else.
maybe an unfortunate choice on behalf of physicists.
Especially because it's
So Emma, I had a question.
Mhm.
So you're talking about these other ways we can describe dark matter with that maybe would give better modeling of our small scale structure. Like how many of those, first of all, how many of those have been shown to give better small scale structure? And then is it possible to still have reasonable large scale structure, or do you just need to primarily have something like WIMP dark matter to give us the large scale structure, and you just throw in a little extra one of these and then you can get decent?
Honestly, I think it's something that's only started to be explored recently. So it's definitely not something that's been like, I mean, the lambda CDM, so that's the classic cold dark matter paradigm, has been the main flagship paradigm for so long. Some people are developing simulations to study some of these other structures. You can see actually that, where's my plot of the simulation? That this like warm dark matter does reproduce the large scale structure pretty well, in fact. And you know, as you make this like a heavier and heavier warm dark matter, it becomes more and more similar to the cold dark matter paradigm. So there are some simulations of this, and they do a good job of fixing some of these problems. I don't believe they fix all of them, but again, it's like an active field of study. It's quite difficult because a lot of these cosmological n-body simulations are these like massive codes that need to be run on supercomputers. So you need to like, you know, apply for an allocation and win that allocation to generate these full codes, or develop the code yourself. And people are still like mostly interested in doing the lambda CDM simulations. And it's only now, especially now that the Hubble constant is also like causing some problems, that people are starting to look at different models to simulate in order to study this kind of thing.
Makes a lot of sense.
Mhm.
Other questions?
I had a quick question on your slide about primordial black holes. I know nothing about primordial black holes. So yeah, so at the top of this plot, we have 100% of the relic density being made up of these primordial black holes. And so there are these, I know you kind of downplayed this whole space as largely being excluded, but there are these two ranges there that seem, if I'm reading the plot correctly, unexcluded. Is there any, again, I know nothing about how you would try to find that or constrain that, but can you say a bit about those spots there?
That's a really good question. Yeah. So like this, I can talk a bit about the exclusion ends. So like here is basically the gap between limits from the cosmic microwave background and limits on large scale structure. So you kind of have a sweet spot here on heavier primordial black holes that, you know, haven't been excluded yet on any level. And then as well for the much lighter primordial black holes, in between lensing experiments, they're basically not massive enough to create sort of micro lensing things that you can observe. And I don't remember what, maybe I haven't written what EGB stands for.
But I guess
from evaporations, yeah, because they would if they're too small, basically, then they would do Hawking radiation, and you would be able to see them, so they wouldn't be invisible anymore.
Oh, interesting. Well, so I guess like on the right hand side, that gap, the CMB constraint, would better CMB measurements allow that to be pushed over a little bit?
Yes, I would say so.
Cool.
And we're expecting CMB measurements. So people are doing like all of these combinations. We're having all of these large scale surveys come up as well. So we're expecting also constraints on the CMB to be getting better and better over the next decade. Yeah.
Cool. Thank you, Emma.
Cool, thanks. Yeah, I was wondering that as well. Any other questions for Emma?
If dark matter were selfly interacting, how would you measure it experimentally?
Interesting. So what I would really love to see is someone putting self-interacting dark matter into a cosmological simulation, because then we might be able to measure its signal in this BAO spectrum. It should also maybe have some kind of effect on the CMB. Otherwise, I quite like self-interacting dark matter, but there are so many different submodels of sorry, I stopped looking at the slides. So many different submodels of self-interacting dark matter that, I mean, you could sort of pick one specific model of like dark pions, for example, where you have some dark sector that's a little bit more like, where they act a little bit more like quarks, and then maybe come up with some kind of experiment to test like that particular model. But I think it would be very difficult to exclude all self-interacting dark matter.
Thank you.
Mhm.
Great. Any other questions for Emma? All right, awesome. Well, thank you, Emma, so much. You definitely got, I think, an unusually large number of questions from the crowd today. So thank you for such a great and engaging talk.
Yep, thanks for inviting me.
Bye, all.
See ya. Thanks.
Okay, thanks everyone. Bye.
Thank you.
Bye.